Hey guys, and welcome to Chem Squad Chemistry. This is Mr. Mullins on the stick today. Our topic for discussion today is going to be the atomic mass. More specifically, we are going to learn how it is calculated. As you may have already talked about in your class or as you watch the other videos, every single element on the periodic table has a few things given to us. Let's take zinc, for example. We know that the top number given for us here is the atomic number, and it tells us the number of protons, whereas the bottom number is the atomic mass, and it tells us the protons plus the neutrons. It's just a little review from what you may already know. Today in our video, we are going to spend more time talking about where this number comes from and why it happens to be a decimal. You may have already learned that it is impossible for you to have a half of a proton or half of a neutron. So we need to learn where that decimal comes from. Today we are going to be using an equation. So if you have a formula sheet, you may want to go ahead and write that down. I will write it out, and I will also show you how I shorthand it to make it easier for me. The equation is going to have to deal with the average atomic mass. Some people call that relative atomic mass. It can be abbreviated average atomic mass, or RAM, as a lot of people refer to it, relative atomic mass. And that is equal to the sum of, this is the sigma symbol, percent of each isotope multiplied by the mass of each isotope. And because we have a percent in this problem, we are going to have to divide by 100 at the end to get rid of the percent. When I simplify this formula, I simply just write RAM is equal to the sum of percent iso multiplied by the mass of iso. Just makes it a little easier for me to keep up with. We're going to be using this formula in order to determine the relative atomic mass, which are the masses shown to us on the bottom of each element on the periodic table. So let's go ahead and get started with that. For our first practice problem, we are going to be talking about chlorine. And as you notice on the periodic table, you can go ahead and get some of your information from that. We have, this is what's given on the periodic table, atomic number of 17, and it gives us a mass of 35.45. Our goal today is to prove this mass using the data that we have been given or that we have collected. You notice that the data that is given here, it tells us that chlorine 35 has a percent abundance of 75, whereas chlorine 37 has a percent abundance of 25. What that tells us that imagine if we were to have 100 chlorine atoms in a bowl. 100 chlorine atoms in this bowl. If you were to stick your hand into this bowl and grab one chlorine atom, let's just say we take one atom out of the bowl, it is a 75% chance that that atom right here is chlorine 35, meaning it has a mass of 35. Let's say you stick your hand back into the bowl and grab another atom. There is a 25% chance that that atom is chlorine 37. It would be this chlorine right here. This just shows us how often these isotopes appear in nature. You can recognize that these are isotopes because of the atomic masses. Remember that protons are not allowed to change without changing the element, so it must be that chlorine 37 has 2 more neutrons than chlorine 35. With that being said, let's go ahead and use our formula to determine the average atomic mass. Remember that when finding the relative atomic mass, or RAM, we are going to be using the formula. Relative atomic mass is equal to the summation of the percent of an isotope multiplied by the mass of an isotope divided by 100. In this case, we notice that we have 2 isotopes, chlorine 35 and chlorine 37, so there will be one addition problem here. The first thing that we're going to do is simply plug these numbers into our formula. We see that our first isotope has a percent abundance of 75%. Just going to plug that straight into our formula here. And it has a mass of 35%, so 75 times 35. We are going to use the summation symbol to add that to the next isotope, which has a percent of 25 and a mass of 37. But if we were to have more than just two isotopes, we would continue this again for every single isotope. Because these are indeed in percent form, we need to divide by 100 to cancel out our percents. So with your calculator, go ahead with me. Let's plug this in to make sure we're getting it correct. It may help you to put percents around these parentheses around these problems to make sure it is doing the correct order of operations. Now, if we plug this into our calculator, we should have gotten 3550 for the top. And after we divide that by 100, we would get a 35.50. This is our relative atomic mass. You should notice that this number is very close to what was on the periodic table, 35.45. That is exactly what we are trying to get. It is okay that the numbers are not exact, because not all samples are the same. Sometimes you may take samples in different places. You may need to take more of a sample to get this exact number. Let's try another problem. All right, so here is another problem. It is a word problem that I hand wrote, obviously. Sorry for the sloppiness. But let's go ahead and get started on it. It says that neon has three isotopes of masses 22, 21, and 20. If the isotopes have the abundance 8%, 2%, and 90% respectively, what is the average relative atomic mass of neon? So again, if you have not memorized it already, you need to remember that RAM is equal to the sigma symbol, percent of the first isotope, multiplied by the mass of said isotope. And if it is in percents, we need to divide by 100. So in this case, our problem is in percents. I like to do a little bit of side work to make my problem easier. I'm going to do that over here on the left. We have neon 22, neon 21, and neon 20. This problem was nice enough to tell us that they were isotopes, but we really didn't need it to, because we recognize that the mass of all of these neons differ, showing us that they are isotopes. They must have a different number of neutrons, because that's what an isotope is. Let's go ahead and figure out our percents. It says if the isotopes have the abundance of 8, 2, and 90% respectively. So I'm going to go ahead and write those down here. And we see that it looks like neon 20 has the highest percent. That tells me that if I were to collect a neon atom, I would expect it to have a mass of 20. It would happen 90% of the time. That's not to say that they can't weigh 21 or 22. It would just only have a 10% chance of that total. So doing this helps me to know what my number should be close to. Because my mass of 20 has the highest percent, I would assume my number is going to be somewhere close to 20. We can also go ahead and take a look at the periodic table, and we notice that neon, which is number 10, on the periodic table has a mass of 20.18. So we're shooting for a number somewhere close to that 20.18. Let's go ahead and plug our numbers into our calculator. We have our first percent, which is 8% right here, multiplied by 22, the mass, plus 2%, the mass of the second isotope here, multiplied by its mass, which is 21. Plus the mass of the percent of our third isotope, 90%, multiplied by its mass of 20. We are going to divide all of that by 100 so that we have gotten rid of the percentages. Go ahead in your calculator, practice typing this in, and I'll give you the answer in just 1 second. If you plug this into your calculator correctly, you will end up with 2018 divided by 100. When you do that, you end up with 20.18 is our relative atomic mass. We notice that our answer that we've got from our calculations matches the answer that was found on the periodic table, showing us that we were indeed correct. Let's try another problem. As we see in this problem, our information is given to us a little different. It says if 69 Ga and 71 Ga occur in the ratio 62 to 38, calculate the average relative atomic mass of gallium. So Ga is gallium. We also remember that the relative atomic mass is equal to the sum of the percent of the isotope multiplied by the mass of the isotope. Hopefully by now you are starting to memorize and become comfortable with this formula. We do see that 69 Ga is written a little different, but remember this is shorthand for 69 gallium. It's just telling us the mass of gallium there above. So we have 71 gallium as well. They also told us a ratio this time instead of a percent, but you notice that 62 plus 38 add up to 100, so we can treat it as a percent. So 69 is in 62%, and gallium 71 is occurring in 38%. Again, we simply just need to plug this into our formula. This time we only have two isotopes. So we have the percent of the first isotope, which is 62%, multiplied by the mass of that, which is 69. Add it to the percent of the second isotope, which is 38%, multiplied by the mass, which is 71. If you are having trouble typing this in your calculator, try putting parentheses around the first multiplication problem and the second multiplication problem to assure you're doing the order of operations correctly. Again, we will divide by 100 to cancel out the percentages. I'll give you a few seconds to type this into your calculator, and then we will go over the answer. After typing this into your calculator, you should have got 6,906 divided by 100, and that will give us 69.76. If you were to find gallium on the periodic table, it is number 31, gallium, and its mass is roughly 69.72. We notice that what we got and what's on the periodic table is not exact, but it is indeed very close, and this would be all that you have to do. Now, there is a few problems that you can do on your own in our unit packet. If you have yours handy, they are on page 5. There are 6 problems there. Thank you and have a good day.